Hello, my name is Bendall from Springer Nature, and welcome to the first of two panel discussions which we are going to be having today, and which is the culmination of 2 days of intense discussions from 25 of the world's leading roboticists, which we've brought together here into Heidelberg in Germany the last couple of days. The major focus of the last days of discussion and what we will be reporting on today has been the concept of life and robotics, and how robots are there. We use robots to also learn about life and to use the concepts that we learn through these study of robotics to improve and create robots to assist humans and the tasks in our everyday life. This event has been made possible through the generous support of our partners, KUKA and the Queensland University Technology, who have also been part of our discussions and involved in the last day's meetings. First of all, I'd like to introduce you to our panelists. So on my right, we have Ken Goldberg from the University of Berkeley in California, or University of California, Berkeley. Aude Billard from Lausanne, from the École Polytechnique Fédérale de Lausanne. Also, Oussama Khatib, Director of the Robotics Lab at Stanford University. On my left is Bruno Siciliano, Professor of Robotics from University of Napoli, Federico II in Naples, Yoshihiko Nakamura from the University of Tokyo. We also have Ruzena Bajcsy from University of California, Berkeley, and finally Greg Hager from Johns Hopkins University. Thank you for joining our discussion. I hope you'll find it interesting. We'll be taking questions from here, the colleagues here in the room, but also anyone out there in our virtual global audience. If you have a question, please respond to the Twitter tag. And I'll now hand over to Oussama to briefly provide a little bit more detail on the concept of life and robotics.
Thank you, Chris. Through history, humans have been always interested in creating artifact machines in their image. And the development of robotics really came with this model of the human. However, the development of robotics itself brought a lot of foundations for understanding many aspects of motion, of behavior, of skills that were always inspired by the human. And little by little we found that robotics was not only good for robots. Robotics allow us to understand better articulated body systems, to understand human and animals and many creatures that are in life. That understanding and the body of science being developed in robotics brought us to think, well, maybe now it is this cycle that we are closing between life and robotics and life. And this was the prompt for this symposium that I should say brought one of the best representation of the expert in the field of robotics and life. In fact, we are so pleased that our colleagues joined us here in Heidelberg, took time for this intense 3 days discussion, and I'm sure we are going to have more discussion in the rest of the day today to conclude and hopefully bring this to the whole community. So let me just pass the microphone to Bruno to bring about other aspect of this organization. Bruno?
Yes. Thank you very much, Oussama. And as also Chris said in the intro, we wanted to make this symposium, which ran for the past 2 days, as lively and as fruitful as possible. And then we organized our scientists into 4 working groups. The first one, you will hear the reports, the summaries from these working groups. The first one was a working group on knowledge, which was aimed at building knowledge by understanding the skills and strategies that humans, animals, and plants employ. And besides Aude, Billard, who is going to report about this working group, I'd like to acknowledge the contribution by Alain Berthos from Collège de France, Raja Chatila from Université Pierre-Marie Curie in Paris, and Peter Cork from Queensland University of Technology. The second working group was focusing on design, which is the natural way to apply this knowledge to design better machines and better robots. And besides Yoshihiko Nakamura from University of Tokyo to my left, also the group took advantage of the contributions by Aline Albuschafer, who is the director of the Institute of Robotics and Mechatronics at DLR in Oberpfaffenhofen in Germany, Tamim Asfour from Karlsruhe Institute of Technology, who is almost local here in Heidelberg, and Antonio Bicchi from University of Pisa and Italian Institute of Technology in Genova. The third working group was on interaction, and the thread was to understand and to speculate on the human-robot interaction as well as on the human augmentation. And besides Ruzena and Greg, who are representing this the work of this group, I'd like to acknowledge the contribution by Nancy Amato from Texas A&M University, as well as Etienne Bourdet from Imperial College in London. Last but not least, and even more importantly, we focus on impact. And as Chris said in the introduction, the goal was to analyze not only the societal impacts, which are obvious when we come to using robots one day in our society, but also a number of ethical considerations. And besides the report by Ken Goldberg, the group also featured Roland Sigvart from ETH in Zurich, Jean-Paul Lemonde from La CNRS in Toulouse, France, Daniela Russe, who is the director of XAIL at MIT, and last but not least, Guglielmo Tamburini from University of Naples, Federico II. We worked, apart from these working groups, we really worked together. And also, I'd like to acknowledge the contributions by Richard Hodson and Owen Vaughan from Nature, as well as Jonathan Lowe from University of Kent and Angela Jayaprakash from Queensland University of Technology. So I think now we will hear the summaries of these working groups, and then we will just continue the discussion.
Yes, so we're going to start talking about the report or what has happened in the knowledge team, and reporting on that is Aude Billard. Aude, so something which also Oussama mentioned in his introduction as well was a major theme is how we use robots that can be tools for engineers to better understand biological life. Could you expand a little bit on that concept?
Thank you. Certainly. So the first thing that we discussed at length was the fact that robots are machines that need autonomy, and to be autonomous, then you need knowledge, and you need to acquire this knowledge in the first place. And so in order to acquire this knowledge, we started toying about the idea of, can we acquire it completely? Is learning the tool the solution? How much do we need to already have laws of control, laws of autonomy? And what does that mean to have laws of autonomy? How much do we need to know about the kinematic of the robot, the dynamics of the world? How much do you know about the body of the machine and its environment? So knowledge, learning, how do they go hand by hand? This was a lot of our concern, and we tried to discuss how to have lifelong learning, having machines that continuously learn, relearn, adapt, and how can we store this knowledge. But the most important thing for us was that robotics is a science that provides information to science at large and to biologists potentially, and to humans. And so we need to be able to extract the knowledge that our robot learn when they interact with the world in a way that is interpretable for human beings. So this was a key concept, the interpretability of what is learned and what is programmed in the robot. And we struggled with problems as to how to make this interpretable. What does that mean to have a communication system with the robot? We also discussed a lot about the dichotomy between brain and body. We love the idea of saying that we have brains and bodies, plural, the fact that we have different type of robots. They don't look the same. We have some of them, they are tiny, they look like insects, others look like humans. They have different bodies. They may have similar brains. We go back to the learning and the knowledge. So do we have similar algorithms? Yes, we do. Do they get to be changed as the robot learns, as the robot interacts with the world, or as the robot gets to have some knowledge about its own body? And so these are more questions than answers, and we love the fact that we are creating problems with robots in a good sense. So we are asking questions, and we are turning to biologists to help us answer some of these questions.
Exciting problems, always.
Yeah. Oussama, I know you've talked about some examples in this direction before. Perhaps.
Yeah. Well, let me have your microphone. Actually, while you're talking about the diversity of robots, you could think about the diversity in biology and life, and that diversity is what also really interesting. I mean, in terms of behavior, interacting with the physical world, I mean, dealing with the resources and moving and using tools and doing all kind of things that we see both in life and in these artifacts, these amazing machines that we are building. That are bringing that also interaction between among themselves and with human. I think probably one of the most important aspect of understanding is how we can translate and encode that into things that can be used by those machines. And I think the team in design was the one who was thinking about those issues. So I would like to hear from the design team, and maybe I'll give you back the microphone. Thanks.
Yeah, Yoshi. So yeah, as you said, yeah, your focus was on design. Yeah, what were the main topics that came up?
Okay, so in the design team, we discuss about many aspects of design. But first of all, I have to point out that design is hierarchical system, and there are many levels of design. And we just listed up 4 major keywords to describe the current and future importance of design. The number 1 is the creative design. The design does not only mean to choose appropriate components and make a system. It includes creative activity to listen to spoken and unspoken voices of society and people, and abstract and put them into the specification and the development of a system. This is very important creative part of design. The number 2, the human life and biology. The robot in and for human life needs human models implemented into various levels, from anatomy, behavior to cognitions. The knowledge of biological system provides direct and indirect living examples of principles, functions, and structures for the design. The number 3, this is a new keyword, but holo design, or model-based co-design. The global scope of the key of robotic system design. This is a global scope. The physics, including geometry, kinematics, and dynamics. Mathematics, including planning and control. Use of models of human behaviors and data structures. They must be considered and optimized concurrently. This concurrency is a very important part. The interoperability of components of hardware and software is a requirement to make this holo design possible. Number 4, reinforcement of interdisciplinarity and societal conquering. The creative paradigm of robot design finds significant challenge in contributing tools for scientific research, and building hypotheses for biological systems, including human activities in the society. The societal attachment and the collaboration with the industries are to be reinforced in the robotics research. The interdisciplinary research should even more promoted in academia. The publication environment does not exist for this interdisciplinary field. The publishers and the expert of reviewers in interdisciplinary research should grow in this field.
Thank you, Yoshi. I think I wanted to touch back on one of those points that you made because it's related to the previous topic as well. And that is the topic where through robot design, you're coming up with models, which are then can be hypotheses that can be tested by biologists and other sciences. And that was coming back to the previous point in that we were building knowledge through actually designing robots for a wide range of not only physiological but also societal, behavioral, and psychological studies as well.
Well, I mean, the two of them are completely connected. So think of designing a robot that doesn't have any sense of touch, and this is what we've been doing for years. You're very limited in what you can do. You can only position yourself. It's like having a robot that is completely blind. Then it's going to be also very limited in terms of the navigation capability, the prediction capability. So you need to design the sensors and the body and the actuation, but assume that you design a robot that has all these tools, all the tactile sensing, all the vision, and then you provide it with a very simple algorithm that all it can do is just moving forward, left and right. And it's not capable of using the sensor or adapting to the noise or modeling the noise of each of the sensor or having a different clock. And it's just, you know, it's an algorithm that runs at 10 hertz and every of these sensors runs at 1000 hertz. It's just wrong. So you need to design both in combination.
And that once you have all those sensors and everything, I think one other point which you were talking about is also the learning part and the robot in context in the environment, and how that is important for robots to evolve basically.
So one of the challenges in the physical interaction, as just Aude was mentioning, is the fact that we need to interact with the world, changing, assembling, putting, making contact, and doing that at multiple points and in very challenging ways that humans do. So we look at human and we see human skills. Human skills are amazing, but how can we get the robot to do those skills? It means that we need to understand human. So now suddenly we want to understand human. We go and start to model and put more information in describing how human is performing those tasks, how muscles are moving and producing forces, how compliances are produced, and all these different things. And suddenly what we realize is that these things are very useful actually for human, more than maybe what we are trying to do for understanding a skill. So this is the process that we've been going through, that was to develop musculoskeletal models, to really track motions and try to isolate vision from tactile and try to understand how humans perform different tasks. And by repeating these different things, we get insights into human behavior that are very, very deep and interesting for human, not only for our task of getting those skills from the human. So at the same time, some of the control methodologies human use or life use was amazing for us in terms of how we can capture that and map it to the robot, to the machine, simplify many of the challenges that we used to have when we were rigidly exploring every aspect of the motion of the machine. Human move fluidly in ways that makes the natural motion really surprisingly amazing to the eyes, but if we look what is behind it and what kind of abstractions the human is using for those motions, we can reproduce that in ways that are much simpler actually for the machine. So this interaction is what is really remarkable, the interaction between what we observe in life, what we can map to the physical world through these artifact robots we are building, but there is a science that is created through robotics, building those algorithms, understanding, and bringing back to contributions to human betterment. And I think that is what is really exciting.
Yeah, so I mean, a few times there you mentioned the term interaction. So robots interacting with their environment, so that they can perform, perform other tasks within the environment, but also talking about how humans interact with the environment, and more importantly is how humans and robots can interact together. And that was the topic of the third team, where Ruzena and Greg were involved. So I'd like to ask Greg, so what are some of the key topics that came up in the interaction group?
Well, so we echoed, in fact, many of the themes that we're already hearing from some of the other panels. We're really in our mind, at the beginning of the age of interaction. It's really, I think, a very new concept that we start to think about designing robots to be fundamentally interactive systems with people. And so when we started to think about the scope of interaction, we've talked a lot about the physical world and about how one would interact with the physical world and how a robot would interact with the physical world. But there's also, as you suggested, there's the social realm of interaction and ultimately the cognitive realm of interaction. So it's not just exchanging energy and force between people and robots, but ultimately it's moving in a friction-free way among people and then finally exchanging information with people that's essential for a robot to perform its task. And so as we thought about those areas, and we thought about the fact that increasingly we're going to design for people in mind, we had a few principles that we thought were really important for the community to start to articulate and to work through. So the first is what does it mean for a robot system to be safe? So at the physical level, what does it fundamentally mean to work with a robot that's safe? And the field's made some progress in that direction. We now have human-safe robots operating in factories. But then, as you move up the hierarchy, what does it mean to be trustworthy? What does it mean to understand a robot system and to trust its capabilities and understand its capabilities? A part of that is transparency. How do you understand why a robot is taking the actions it's taking, and are those actions understandable in the context of how a human, for example, would understand and perform a task? And finally, what does it mean for a robot to be socially acceptable? We had a longer discussion about the question of to what extent should robots emulate people and act like people, and we should be trying to design toward that type of social interaction, and to what extent are robots a fundamentally different entity. And really, when we think about design principles, we should be thinking about designing towards principles that are reasonably unified and common across robots that again, give people comfort that robots interact in a certain way in society. One of the other observations about this is that right now, much of the work in these different areas, you think of the physical, the social, the cognitive, it's really happening very much in isolation. There are people who focus on social robotics, there are people who focus on the physical level of interaction, more on the AI level and communication. But there's not really yet threads connecting them. And I think one of the grand challenges as we move forward is to understand how do we connect the physical, the social, and the cognitive in meaningful and generalizable ways across applications. Another theme that again I think echoes the other panel is the notion that as we advance the science of interaction in robotics, we're going to advance the science more broadly. So think, for example, of psychological science or social science, where you're developing theories of interaction, or you're developing theories about how groups interact. Right now, that's a science, and you study and observe and you build models. But robotics is an opportunity to deploy those models and to test those models. It's a way to build artifacts, and it's a way to build new tools and new forms of understanding that in fact will also advance the science for our colleagues. And so as we move this field forward, I think the opportunity for kind of enlarging the tent and bringing in social science and even humanities into the science of interaction is going to be a huge opportunity for robotics, and also an opportunity for, again, the broader scientific community. So those are at least some of the main themes that we touched on in our panel.
Ruzena, would you like to add to that?
Well, I just want to add, to me, robotics is all about the robotic science. And its hallmark is the integrative and the methodology that we develop, which is we make a hypothesis, then we design experiments or just simply make measurements, build models, then we build test beds, and then we validate our models. This whole chain of methodological steps is extremely able to predict scientific results on multiple scales, starting with molecular, then organ level, body level, and even at the societal level. So in that sense, to me, robotic science can reach and be part of a much bigger activity of scientific endeavor.
Well said. I wanted just to make a historical note about the fact that the interactivity between robots and human started at the beginning of robotics, when the first robots were simple enough to be teleoperated. So human, I mean, these were the first robot, and the human would interact with those robots, controlling all the joints, and they're doing one-to-one motion. Robots became more capable, more complicated to be controlled, and more autonomous. We went all the way in industrial robotics to completely isolate the robot, but by structuring the environment and program in details their motion to do the production, and we have now millions of robots working around the world. But I think what is really new about this era of robotics is the fact that robots are not anymore in the cages, and robots are out interacting with the human. And the science of that interaction is so critical. So critical, and these robots are going to be very different from the industrial robot. They have to be safe, as we said, but also they have to perceive intent, and they have to understand so many other things than just running through a program or pre-programmed behavior. So this is really interesting. We're going back.
Emphasize the scientific methodology. Yeah. That we have to go through is applicable in many different areas of science. And the critical point about robotics is that we not just model, but we also physically have to interact with other robots, with people, with other environment, and that physical interaction reveals new phenomena.
Absolutely, absolutely.
So actually this topic which you just brought up, co-robots, collaborative robots, is also something which is a major theme from the impact group. Maybe that's a good place to start, Ken, and telling us a little bit about what was discussed in impact.
Thank you, Chris. Well, robots have had a long history in our imagination that precedes the science and the research, and they really operate very interestingly as a metaphor about what they can reveal about human nature. So the group looked at stepped back a little bit and thought about how they're positioned in terms of society and social impact. And one thing that we really we spent a lot of time on was the very popular headlines these days about the future of work. in even some very distinguished publications, are reporting that robots are on the verge of stealing many jobs. And there was a almost universal consensus here at the meeting that we're quite skeptical about these predictions. That despite the recent advances in computer vision and speech recognition and game playing, I mean, certainly it was a breakthrough that we were able to. The AI is now able to defeat the world champion in Go, and these are beautiful results. And the entire area of deep learning is very exciting. And also, there's been a huge investments, unprecedented investments in the industry, including all the tech industries in AI and robotics these days. But this does not necessarily imply that we will soon have human equivalent robots. And we feel it's important to convey that because as Ruzena just mentioned, the physical interaction with the world is quite unforgiving. And that the ability to manipulate and control contacts and the forces of nature are extremely difficult and have resisted our ability to formulate and to have reliable robots. So, and a key issue is the fundamental uncertainty in the world. That despite all the advances in sensing, that we still have to cope with the fact that we don't know the precise positions and orientations of everything in the environment, and that those minor errors can actually lead to quite catastrophic results. So we want to push back a little bit on this expectation. So for example, the idea that truck drivers will are going to lose their jobs, that all truck drivers will be eliminated shortly. We're very skeptical about this. The sense is that probably on the freeways it will be true, but not necessarily on city streets, and that at the same time, we also want to be respectful of the issues, of the concerns, that if there are advances that we don't anticipate, we should be keeping a close eye on those evolving on those technologies. And so we should look for signs, and this is where the communication is very important. And the research has accelerated dramatically in this field to the point where new results are being shared almost daily and in a number of different venues. And so that's very important because for all of us to stay aware of breakthroughs and developments, because it is important that we share this and alert each other and our colleagues if there are advances that we think will trigger this kind of widespread disruptions that are being predicted. So that was the very big concern from the society perspective. We also see a huge potential, as has been mentioned earlier by Greg and others, about the co-robotics, this idea of robots working together with humans, and that this is the idea. Instead of thinking about a singularity, we might posit a multiplicity where people and AI collaborate in new ways. And in fact, AI may help us understand the importance of collaboration in new ways. We think it can reduce tedium in many applications, including driving. It can increase safety for human drivers. We certainly think that is going to be the case. And also, it will improve performance, for example, of surgeons, who may be able to use robots in an assist mode to perform surgery with more accuracy. So we see a lot of potential there, again, for robots to enhance human work. And then the other two are that we are acknowledging the aging population in almost all countries, and the need for robots to be able to assist in homes. So one that we discussed that we believe is within reach in the next 10 years is the idea of a robot that will not only just will clean the floors, but will actually declutter, pick things up and put them away, which could have a great value for senior citizens. And we believe that this is possible, and will probably, the prediction was that it will be an auto company, because auto companies are very good at managing designing complex systems, producing them at reasonable costs, and also provide the service centers to be able to service such devices. So we think that could be done within a price range that would be accessible to most senior citizens. And then the last thing we thought about was the idea of robots, the potential for robots to inspire the next generation of engineers. that they are that we think more needs to be done and to think about how to design robots that could be used for teaching, and particularly that would attract a diversity of engineers of different genders, of different backgrounds, because we see that that is going to be so important for the robots of the future, that we have a diversity of researchers who are contributing to their design.
Thanks, Ken. I'd like to touch back on one of your topics and what was discussed here previously when it comes to actually having more robots in our lives was the concept of trust and what we expect robots to do for us. And especially when something has a degree of autonomy, suddenly we expect it to be able to do so much more than our washing machine does. This concept of trust and what expectations, I think, was very interesting in the interaction group.
Yeah, well, yeah. So as you suggest, as we see increased complexity in systems, one of the things we find, and in fact this emerges in user studies too, is with a complex system comes an increasing difficulty for users to build a mental model of what the system might or might not do. Part of what allows us to trust each other or to trust your car when you're driving it or your washing machine or whatever is, you trust that when you press on the brake, your car is going to stop. And you have that model in your head, and you can kind of use that as a basis for your driving behavior. You trust other drivers are going to generally adhere to the laws, traffic laws, and so you can use that to govern your behavior. So as robots become complex and as they increasingly interact with us, trust is going to emerge in some sense from our ability to predict what they do. And I think one of the interesting aspects of that is as they enter more and more safety critical applications, we're talking about autonomous driving now, you're talking about, Ken speaking about elder care, now you're talking about robots interacting in an intimate way with people. And so the level of trust really has to be very, very high for us to be able, for the public to be able to accept those systems. And conversely, I think the contrapositive of that is safety. These systems have to be very safe so that we don't run the risk of losing public trust in systems due to inadvertent actions that may have been unanticipated by designers. So I think the notion of how do you build trustworthy systems that are transparent, predictable, and safe is a fundamental issue in robotics.
Well, I just want to add to that, because one of the things that is that's the big new wave of excitement right now is around deep learning, and it runs counter to the traditional approaches of robotics, which are based on analytic models. And for analytic models, we can have very nice predictions. We can often prove guarantees on their performance and bounds on their behavior. But this may not be the case with deep networks, and that I think it comes right to this trust question. We want to be able to trust these systems, and we need them to be able to be analyzable, and I think that's a huge forefront for research.
Well, related issue, just you mentioned deep learning and kind of more complex systems that are black box, they're not transparent. A part of that is also, can we start to design systems that have an understanding of their own capabilities and are able to communicate what they are and are not capable of doing and why? Because again, that leads towards the trust issue. It's one thing to do something wrong, it's another to say I'm incapable of operating in this environment and here's why this is the limitation of my behavior.
Yeah, I'd like to elaborate the concept, and I think it's like what the research community is currently tackling is also to find quantitative and objective metrics for safety, dependability, trust. It's like, and to this extent, I think our mission should also be that of promoting systematic benchmarking in robotics, which I think, this has been proposed at various levels in research projects, but I would foresee a sort of a strategic effort by the community, because if we want to develop such systems on an industrial and commercial scale someday, sooner or later we have to tackle this, and I think it's our role really to find just usable tools to assess the performance of cooperative robots with humans.
Indeed, one of the really interesting thing from this discussion is that we see that, well, we need safety and we need to guarantee safety, which means we cannot really make use of the same design concept that we were using in industrial robots. And today, there are so many robots today around the world are rigid because they need to be precise, they need to be accurate and fast, efficient. Now we have new concepts that are being little by little brought together into the this idea about human-robot interaction. So we talk about soft actuation, we talk about soft robotics in general, and we are bringing new way of putting different actuation systems, skin, and all kind of new designs that would be suitable for that human-robot interaction. We have to guarantee it, which means that it's not enough to be safety through software or safety through some sensors that could fail eventually, but we really need to have full guarantee that that interaction will not cause harm to human. And I think these are really interesting challenges that are bringing a lot of novel research in sensors, in material, in ways of integrating mechatronics and molding all of these together in the hardware of the robot system. So.
I just wanted to say I really reject approaches that say, look, Ma, it works. Not good enough for me. We are engineers, and we are obliged to find the boundaries and say, within these boundaries, I guarantee it will work. And I guarantee you because, and I know that because, this business that it works and we don't know why it works, I don't buy it.
And actually, an important part of that, Ruzena, is also that it's our duty to also share where it doesn't work and demonstrate the failure modes very clearly.
Of course, if you know the complementarity, you know, my famous question in PhD exam is, okay, you told me what works, now tell me what it doesn't work.
We have a whole conference devoted to validation, and we appreciate always papers who bring, well, the theory doesn't work really in here. And I think this is very important.
So yeah, we have another 8 minutes of our panel discussion. I also wanted to come back to one thing which was mentioned in the interaction part, and that was how, you know, robotics as a discipline or as a science should become more inclusive as a big tent for many diverse areas of humanities, science, and engineering. This was also a topic which was brought up in the knowledge section, where the concept was that we really need to have people with other skills interacting in the area of robotics. Or did you want to pick that up?
Sure. So we really brainstormed the fact that we have to learn a lot from how humans develop and develop these skills that we so much want to have in robots. And I think this has been mentioned before, that we want to have robots to be very flexible, adaptive, learn. And, you know, these are keywords, but we certainly don't know how humans really do these things. And so there are other disciplines such as developmental psychology, biology, even, you know, ethics and philosophy that study this at length. So bearing in mind that we want our engineer to understand what they program, we still believe that they need to have a very strong background in math, physics, and all of those. But we like also to have them, you know, get exposed to this other discipline, whether it's during their PhD with having really programs that are jointly organized between biology, psychology, and engineering fields, or having longer stay during the postdoc and afterwards. So we believe that this is absolutely necessary for the field. But once more, stammering in that we want our engineer to understand the math and the algorithms behind before they go and move and use other tools.
There's also the converse of that, though, which is, in the future, you would like to believe that perhaps, psychologists, sociologists, ethicists might actually embed themselves in the robotics community and bring their ideas into the community and seek to understand robotics. One of the things we talked about is, in the future, will you actually start to think about things like, engineering ethics or ethics engineering? Or psychological engineering, or social engineering, where it really is a hybrid of the field. It's not just kind of our students learning about it, or maybe them coming and giving us some ideas, but it's really a deep embedding and a cross-fertilization. And I think that's really an opportunity for robotics at this point.
Yeah, this was...
Can I make a comment from design point of view? So the biological system or societal system is hierarchical and very complex system in multi-scales. I think the robotics has a very strong tools for modeling the complex system and connecting the systems of different scales. And if we are missing some knowledge, of course we want to have all the knowledge, but if we have something missing, we can make the feasible or reasonable model for the missing area, and we can make the whole system as in the simulations. So I think this is the very strong part of the robotics contribution to society or science.
I just wish to add is this issue of cross-fertilization has been very very strongly felt in the group that gave rise to this long time project of the Springer Handbook of Robotics, because just in which most of us were involved, and the main point was that in the last 50-60 years, I think we have well assessed all the core methodologies and technologies which are enabling the design and realization of advanced robotic systems. I think our attitude as robotic scientists is already that of a wide outreach towards other community. I think we share the common view that further progress in the field will not happen within this group, but as you were saying, will happen at the crossroads with other disciplines, and this is what's happening in robotics, and probably the gradient could be much faster than we might think about.
And I think one other point that we should really stress or look into to finish off this panel is that robots are there to assist, or our motivation for creating them is to help us do things. Oussama, would you like to expand on that point? They're not there to take over our lives.
Yeah, there is a great concern about robotics today in terms of and AI and how robots might really take over our lives, and sometimes we feel in the robotics community that we are flattered by those high expectation of the potential of robots that we are working on. Knowing robotics and knowing the field and the challenges, and knowing how difficult it is to really bring, first of all, the capability to interact with the physical world, and then connect that with cognitive capabilities to reason, and then to get the experience translated in intuition about different actions. The problem is huge. So today's robots are coming out of their cages to interact with the human, and more we are going to see something very simple. Something like we can describe in two words: muscles and brain, and the connection between the two. Muscles are going to be supported by the robots, and the brain supported by the human, and the two are creating a new synergy. there is a lot of brain in the robots and there are a lot of muscles in the human, but essentially removing the pain of a task and reaching places that human cannot reach, and working with the human intuition, experience, and expertise. And we don't want to be operated by an archaeologist. We want a surgeon to operate. So the expertise in human is amazing, and extending the hand of the human to reach in those areas is quite important. So this connection with the human is going to be really remarkable in the way we will be using robots in the coming years.
Thank you very much. So I hope we've been able to give you a bit of an insight into what we've been discussing in the last couple of days, some of the key opportunities and challenges which the robotics community, or the wider community involved in the project, which is robotics. Yeah, we hope you've enjoyed it, and we've certainly enjoyed telling you about it. Thank you very much. Good afternoon and welcome to Heidelberg, Germany and Springer Nature's Life and Robotics Symposium. And today we're reporting back from a few days of intense discussions from 25 of the world's leading roboticists on the topic of life and robotics and what robotics means also for human society in the future. In the first panel, which some of you or maybe all of you have just heard, we heard from the teams that were involved in the symposium reporting back on key challenges, opportunities in research related to robotics. And a lot of that research taking place in academia, but also increasingly in industry. And in this second panel, we want to focus a bit more on, taking these ideas to become actual products and applications in our everyday life, and what is the transition of this knowledge and research from academia to industry to product. A natural progression on from that, as we start to discuss, the role of industry in innovation is also, the role of robotics in industry as well. And we'll be looking at the future of work, Industry 4.0, and some of the ramifications of that. Just to start off, I would like to thank our partners in this event, KUKA and the Queensland University of Technology, who've not only provided generous support for this event, but also have been deeply involved also in the meeting in the last couple of days. First of all, I'd like to now introduce our panelists, starting with Philippe Lorenz. He's from the Stiftung Neue Verantwortung here in Germany. Then we have Torsten Kröger, previously at Google X and now at Karlsruhe Institute of Technology. Then we have Oussama Khatib, director of the Stanford Robotics Lab at Stanford University. Bruno Siciliano, professor of robotics at the University of Napoli. Rainer Bischoff, head of corporate research at KUKA. And Jonathan Lowe from the University of Kent. So to start off this discussion, I'm going to talk to Torsten. And what I would like to understand or like to get would be, what is the role of university research? How does that influence how industry, how information comes to industry to develop new products, and what is this transfer process like, and what can we do to improve this synergy?
Yeah, thank you for kicking this off. I think that there is, first of all, room for improvement on both sides. And now having spent a couple of years on both sides over the past decade, I feel that especially in Europe, universities can do a better job by, first of all, understanding that technology transfer actually means transfer of people. And it's not only patents and IP that is generated in universities, but it's really the people who work on that, who have the ideas, the engineers that are getting trained at the universities, who need to push these ideas forward. Just owning the IP or just owning the source code will not bring you very far. And I feel this is where some universities in the United States, and I feel especially Stanford, is doing a much better job supporting young people to work on their own ideas, to fund them, and just offer an environment where this can be done. Now, on the other side, looking at companies, I think there's a lot of stuff happening in the space of robotics. I think things are improving quite drastically compared to other sections. But especially like large corporations, very traditional corporations, they're very often not open to new innovative ideas. And I feel that there are a number of industries that might get left behind. They are missing out on new business models that are now becoming enabled through new technologies in robotics, machine learning, that have not been possible, let's say, 10 years ago.
So yeah, I would like to come back to one point there. I mean, how you mentioned, IP generation and ideas being developed at universities, and I guess at many universities there is this more and more focus, of course, creating this IP, but also then this sort of creating startups around ideas, and how this then creates products for society. Maybe Oussama, you can talk to that point.
Yeah, actually, I wanted to echo what Torsten was saying about the fact that it is not only IP, but it is really the human, the new researcher that become part of that flow of transfer. The success of the model in the Silicon Valley really relies on a continuous flow from university with ideas and people that go to industry, and then there are all those investments that are coming back to the university to promote more research and more connections with a new project, and then we discover the startup that are bringing the innovations with some of those ideas that end up to become large companies. I don't recall the number at Stanford of startups that came from Stanford University. So this model actually is what is really important about it is the continuous flow of knowledge of new researchers that are interested in themes that can be brought to development within the industry, and I think this is happening. We are doing that in many universities connected to industry, but my experience as director of the Computer Forum at Stanford, where we have about 100 members of companies, has been that also in the distant geographic locations, they are trying to implement models similar to the model that we have in the Silicon Valley, but it is not an easy thing to do, and I think we really we cannot copy models. We really need to understand the nature of the of that environment and how those things can be done. But essentially, I think we need that cycle. We need that flow, continuous flow from industry in terms of support and project, and from the university in terms of people and ideas. Bruno.
May I add something just to stimulate discussion and trying to be a little bit, let me say, provocative. I think this was mentioned by Torsten as well as by Oussama. In my perception, as European researcher, and also, I mean, I know the Silicon Valley, I know the Industry 4.0. I think, the advantage in the Silicon Valley is this kind of entrepreneurial culture, which is felt, especially when the universities they really favor the startups. It's like, but I think this is perceived in terms of companies other than industry, because I mean the perception of the industry, it's more for probably you touch upon this issue, because it's like tradition in Europe has been a lot of attention about how to transfer the technology to industry. When I mean we have here representative from the largest industry for robotics in Europe, KUKA, and this is also the case of other industries. So I think ideally it would be nice to combine the mentality of the Silicon Valley with the core flow and transfer of technology, which has been happening in Europe, also thanks to the funding by the European Commission, which has favored this kind of tight link between, I would say, industry and not companies. I think maybe we need more kind of venture capitalists and more kind of crazy companies. What we are missing here, high-risk company in Europe, which instead is the case there. At the same time, I mean, I don't think there's been, a kind of really link as tight as the one in Europe, in the Silicon Valley, between robotics and industry. I don't know if I got the concept.
No, I would like to strongly second that. First of all, I would like to add to one of the first points you made, that a company like KUKA is already doing a fantastic job, kind of being innovative and working very tightly with academia, with a goal to kind of get research results into the company and into products at the end, so that society will benefit eventually. But I've seen a number of cases, not even crazy ideas, just like fairly down-to-earth ideas coming out of robotics research labs with a solid business model, but it was close to impossible of getting funded in Europe. And this is very different in the San Francisco Bay Area. Right now, I feel it's maybe even a little bit, even on the opposite side, it's a little bit of a bubble. You know, people, hey, I have a degree from Stanford, I want to do robotics and machine learning. That's all you, that's all you need to say. I'm exaggerating, obviously, but these are the ingredients that you would need in order to get funded there. And I think as in many of these cases, the middle ground is probably what is the most healthy and most sustainable in the long run. And I feel that both sides can learn from each other, but I think especially in Europe, there's something where we can definitely improve.
Maybe it's also worthwhile to mention that these government programs that exist in the US that are focused on these high-tech clusters around Boston and the Silicon Valley, these were actually government programs that the American, US government came up with in the late 70s as a reaction to advanced manufacturing coming from Japan. And these two most famous government program, the SBIR, Small Business Innovation and Research Program, and the STTR, the Science and Technology Transfer Program, they provided early stage and middle stage venture capital to small innovative businesses and kept them alive in a way. And these sort of government programs do not really exist, I know for Germany at least, but also in the European Union, such funding that really targets specific cutting edge research and helps to technology transfer to happen.
So I would like to underline what you all said. So I think the most important aspect is to transfer people into companies in order to do the technology transfer. You just cannot just support software or USB stick with the know-how. That's not possible. So you need to transfer the people into the company. But then also inside the company, it's more like that we have to transfer people within our company from the research team that I'm heading into serious development. So there's also a valley of death inside the company. And what we as KUKA also try to do in order to accelerate to get to products, that we team up with little startup companies around the most critical topics in robotics, like perception, and that we try to build together the future on a fast track surrounding the KUKA environment. Because also we have become a little bit bigger by now, and it's also getting hard to push the innovations through our company. Of course, we're doing a good job, but even still, to accelerate this, we try to team up with new companies that we put around our ecosystem.
Well, I mean, that is right, and I think it's not only a transferring people in the sense that we are just hiring. I mean, hiring is very important, and that transfer is one very important aspect. But I think also there is, through this transfer, we really need to think about the fact that we need to have in-house knowledge of that field, that area that we are bringing to the new applications. And that means there is continuous interaction that can take place in form of internship within the companies or exchanges within the university. And I think this is very productive. The idea that we are not just again, transferring programs and passing them, and well, now you can use it, but really understanding what is behind all these concepts and how that knowledge is transferred in-house. And that means longer-term involvement together. So this partnership is very, very critical to successful transfer of technology from academia to research. But I want to mention one more thing, which is very often there are specific problems that industry has in terms of dealing with smaller short-term problems, which we call in academia side the engineering problems. And we have to realize that the academia is not the proper place to do that. That is, we are doing research, we do not want the researcher to be looking at very short-term and too short-term problems. That would be not beneficial to their development and to the exchanges. But I think there is a need to creating that interface, a human interface between academia and industry in a way where we transfer knowledge, we transfer validation and expertise, and then we are able also to bring new hires and new ideas and through that cycle.
Yes, thank you, Oussama. So I think this is really important that we collaborate very closely with each other. And of course, KUKA is also supporting basic research. So we are not just having applied research that we try to focus on, but what you as academics or researchers could consider at universities to look more closely into use cases that come from manufacturing, that come from the industry. So not just make up your own use cases, but try to go out into the industry and see where are the real problems. And I can guarantee you that you will also find challenges, research questions that last for 5 or 10 years. Let's take like autonomous grasping, for instance. You can research the basic research question also if you have an industrial use case.
I think he's optimistic. 5 years is not enough.
I think there's another thing that academia can do better as well. There are some domains where researchers and scientists do not see the chance to create any scientific impact anymore, because this is a field that has been worked on, let's say, in the 80s or 90s, but it's still not in the industry. There's still not a product out there. So we are not producing, in quotes, master students, PhD students that are that get the training on these technologies, but they actually need it in the industry. And just because it's scientifically not interesting anymore, it doesn't mean that it's not important for the industry anymore. Of course, this is on a case-by-case basis. This is not true in general, but I feel this is something where we as academics can do a better job as well.
So that, yeah, related to that is the point of sort of a quality gap and the type of deliverable which comes out of academic research as not being directly applicable to industry. And on one side, it could be focusing on particular use cases which are important to industry, or there are other aspects to that quality gap which need to be considered.
So this is another thing where I believe researchers, especially in robotics, often like to showcase cool robots, nice videos, and that's sexy and catchy, and they get a lot of clicks on YouTube, which is an important media nowadays. There's no question around that. However, to make one out of many concrete examples, there's, for instance, ROS, the robot operating system, which is a framework being used by many researchers in the space of robotics, specifically working on software control, perception. However, from a product perspective, the quality, there's no real time, there's no determinism. The quality varies a lot. It's almost impossible to implement a robust controller. Safety is not even considered. However, if as a company like KUKA, you will need all of these features, and researchers don't really deliver on that, though they claim, hey, I've solved it. And so there's still a big gap, and I think this is something where maybe both sides can kind of try to come closer together to close that gap. And maybe it might also be the time to need a new ecosystem that is just more professional, so that we can do better and faster, more efficient technology transfer.
Yes, maybe to just add to this, so for instance, one example would be safety. So academics usually think that industry will take care of the safety problems later, but as we have listened also in the first panel, it's a design issue. So you have to think about this from the start and not just say, okay, industry will solve the problem. So please think about this from the beginning to embed safety in your things.
So, I mean, in robotics research, there are many challenges, and safety is becoming something very, very critical as we move towards human environment. I mean, that is clear. I don't think the university and the research in the university is going to guarantee safety in as a product. I mean, this is the role of the industry that is going to take it to the manufacturer that is going to deliver it as a commercial product. But I really think that exchange and partnership we talked about requires us to create that interaction between the researchers, the development that are taking place, and the product, the software development, and the systems and the architectures that are developed in industry, to reach that level where both are able to pursue the research and also to have a commercial product. That requires more transparency and openness in those systems. Something that was resisted in the early years, I recall many discussions in the Puma group, the Unimation group, when we started working with the first industrial robots in university. There were a group asking many questions, how to access this and how to access that. So we were talking about open architecture for product that are coming from industry, and that was very critical to many of the development that came later in moving from position control mode to force control and contact and closing loops and adding more sensors and creating more capabilities. And I think this is something that is still sort of in the work, that many companies that are producing manufacturing robots and the software and the controllers are having difficulties dealing with because of the complexity and the challenges of safety that all that brings. So I hope this is something we can address fully. I hope.
You mentioned the concept of open architecture. What did you mean by that?
Well, that is basically in a control architecture of a robot, there are multiple layers that deals with, in fact, where we access the motors, how we close the different loops, how we reach a level where a user can program the robot. And this is usually done at much higher level related to the way the industry designed the interface. Now, if we take this robot and put it in a research environment, we need to access lower levels that are not accessible and open in general. And in part, this is part of what we are commercializing. I mean, this is part of a lot of investment the company is putting in the development of the system, and it is not something that is easily going to become open, but for many aspects of the research, when we add the new sensors, when we want to access different layers of the control architecture, that facility becomes very critical to progress in the field. And we are still struggling with that problem. And I think this is an issue that we brought up over the years in our interactions with the industry, and I think the industry is working on it. And this is something that I hope will be resolved in a way where both the industry and the research could benefit from, but also ultimately the progress of robotics and the progress in applying robotics to society that will be the winner in that.
And this is true not only for industrial robots, like those like Oussama and myself with the control background. Since the very beginning, we felt the need of having an open control architecture for industrial robots, but this is also the case, for instance, for robots for surgery, because like, I mean, the only commercial platform is the well-known DaVinci by Intuitive, and Intuitive has donated now I think it's 30 platforms to the to some robotics labs around the world, and those platforms have the peculiarity of being open. So basically, we could interface some control boards in such a way, as Oussama said, to interface all kinds of sensors, because right now we only have a visual perception, but there is no tactile, there is no force perception for surgery. And in my lab, as well as in other labs, we are studying about developing new microsensors using optoelectronics, using organic materials that we can just test on the platform, thanks to the fact that this platform is open. So this is really a common thread, which started from the industrial environment, but now this is true also for all kinds of robotics applications.
Of course, I can add to this. I mean, KUKA is offering open platforms for researchers. I mean, we have a couple of platforms, and just because you mentioned the DaVinci system, so very recently KUKA has certified its lightweight robot for medical use. So as you know, KUKA is a component provider in the field of medical robotics, but you now can much more easily develop your own product based on a certified medical component from KUKA. So, and that's also important for startups in Silicon Valley that want to come up with new medical products. If they want to base it on a robot system that is certified, please come and have a look at KUKA robots.
So in our previous panel, it was the term singularity was brought up. So the point at which robots take over everything, and how far away in the future that is, and so the time frame that it takes to do this research and create products and get to that point. It'd be nice for our audience from people who've involved in the industry, to a little bit understand this cycle from research to product. What sort of time frame do we have there? What are the challenges or the hurdles that are in the way?
I think in terms of time frame, this can be anything from, I would say, 3 years up to 10 years. So if you take a look at the lightweight robot that we took over as a technology from DLR, it took us almost 10 years to make a product out of this that can be used 24/7 on the shop floor. It's a complete different thing of an extensive use in a research environment and of an intensive use in a production environment, and this has to be taken into account by manufacturers like KUKA. And so it can take long, but we are working on it to get better. As I mentioned, to team up with startup companies that have a much faster way to bring products to the market.
Well, I mean, the short term and the long term, and where how robotics is developing is very interesting. I think robotics relies also on technologies, on computer technology, on the CPU power, on the material, on the sensors and their integration, and a lot of things. So historically, many of those were not available in the 80s. We were not able. I mean, there was a promise of the robot in manufacturing, but it ended up to be a very simple version of a robot doing very fast and very precisely those tasks in a repeated way. There was not much sensing, not much variation in the task. And I think as we start to move with the field, and as the field start to mature, and as technologies, supporting technology came to become available in terms of CPU speed, in terms of new material, new sensors, and new integration, amazing new algorithms and computer power, and new technologies in terms of dealing with that integration, the networks, and removing all the cabling. I mean, before to just deal with some aspect of tactile sensing, you have to think about all the cables that were coming out from your sensors. So all of that that merged into really development that are speeding that cycle. So the cycle, I mean, I recall the mid-90s, we were developing the first torque control robot, and through collaboration with DLR, I don't remember how many years also took really DLR to build the full lightweight robot. It was a process also depending on a lot of new technologies, the motor technology, the actuation. And little by little we are observing that this is accelerating. And I think this is really wonderful time for the innovation in robotics, because many of those technologies are there now, and we are seeing that in many applications in the medical field, in the service area, and in the potential that is coming to agriculture and many other applications in the field. And beside, I mean, the time frame you mentioned, I would be more optimistic about shortening that cycle and in the future. Yes.
Your experience?
I would like to second that. Actually, when you were talking earlier, I was also thinking of the lightweight robot, how it started at Stanford, and then the way to DLR and eventually to KUKA. But there are many more examples like this, where I think even a time frame of 10 years used to be too short in the past. Think of self-driving cars, where like first research maybe in the 80s, and there was a lot of SLAM being published in the 90s, and things got more and more advanced, and then with the DARPA challenges in the 2000s, things then really took off. And now even Google started the project right after the last DARPA challenge in 2007. And now it's 10 years later, and there's still no product available. It seems that we're getting close, but we still don't know when things will become available as a product. So things can take decades, but there's no rule of thumb. But I fully agree that this seems to be accelerating quite a bit, which is a positive development.
Coming to sort of another topic related to industry, but also related to how robots have changed, as you described, from doing very simple, repetitive processes to having many more senses and being able to collaborate more with us. How is, the introduction of more collaborative robotics, how is that influencing now manufacturing, and what are these types of things that robotics companies now are working on to bring to manufacturing?
I think first of all, it's a painful experience for all companies in the field of collaborative robotics, because you have to educate your customers on how to use collaborative robots. So also our, let's say the salespeople, they have to be educated, okay, you do not sell this robot by its payload and by its reach, but you sell it by its features, that it can work without fences with a human, that it is sensitive, and that it can do many different things than our stiff and very precise industrial robots were used to do. So it's an education process of both the salespeople, but more so of our customers, because with a lightweight robot, torque controlled, sensitive, you can really change the production paradigm. And that is something that no one really had prepared, and I think that we are still educating our customers on how to use the robot.
But what is also the potential now for collaborative robotics in manufacturing? Is there really a major movement there at the moment, or is it still a ways off?
I think there's a huge potential, because what you get rid of is the fixed fences that you have around your robot systems. So human-robot collaboration really opens up a path to more flexibility in automation, and also maybe using less space. If you don't need fences, you have less space, and you can much more faster reconfigure your whole production. And producing a mobile phone, for instance, you only need it for 3 months to ramp up or to have the full production capacity, and then the next phone is coming, and you need to reorganize your whole processes. You need to reprogram. You don't want to have these fixtures, these fences that we have today. You want to have robots and humans coexisting on the production line. And of course, you want to have a collaboration between humans and robots.
Yeah. Bruno. Yeah, I think it's exactly the issue of customizability. Just as like I think like cobots will really break it through when users will be able to operate them, plug and play, without without going through the instructions. So it's like our kids. They operate smartphone, tablets, phablets, and it's like, in a kind of totally intuitive way. So I think the future workers in industry, in a few years, they will be able to customize and just any kind of operation
in a plug-and-play mode, as intuitively as possible. This is when I think cobots, of course, it's like all the safety, the standards, of course, they have to be addressed in the most functional manner, but that is when I think this will become a sort of like using any kind of appliances.
Yeah, I was going to say also that then probably this robot would reach the mid-size and smaller company that are not able to afford the assembly line, the very expensive assembly line that we need to have. So basically, instead of moving the product, adding component on the assembly line, what we are talking about in the future generation of manufacturing, we will don't have to use all these fixtures, all those costly components that structure the assembly. Rather, we are going to use more flexible mobile manipulator platforms interacting with a human, where the human is guiding the orchestra of these robots to build the product in a much more reprogrammable way, much more easy to interact with way, and which would make it much more affordable, which means we can change the design very quickly, which means that also a smaller company can afford it. Now the challenge is addressing and bringing those capabilities, starting with the safety to dealing with the sensory information, dealing with the easy to use. The easy to use is still a challenge. How those systems are programmed, what kind of skills they have, and I think the new generation of robot that brings torque control capabilities, force control, contact, and compliant motion primitives, and all the behavior of dealing with constraints and obstacles and self-collision. All of these techniques that are being developed today all around the world in the robotics laboratory will come to be part of those systems, and that will transform completely the robot concept. Actually would bring the robot back to what we wanted to or imagine we could have done when robots were first introduced in manufacturing, but no of those technologies were ready at the time. This is happening now, and I think that is going to completely change the way we use robot in manufacturing.
Yeah, the way we work. So that sort of brings us to our next major topic. And as we go along, I just want to remind our audience that you're welcome to ask questions via our Twitter tag, SN Robotics. So yeah, it really brings us to the topic of future of work. So how, and when we talk about future of work, in this forum, we're talking about robotics and so very much focused on more the manufacturing sector rather than artificial intelligence applications, which would be more the service side of things. So here talking about how work will change in manufacturing with the introduction of more complex and collaborative robots. And I guess in general, what does it mean? And there's a lot of discussion and there's a lot of fear as well. But as we've seen from history, that most the other industrial revolutions actually brought positive effects to the way people worked and to society. And I'd just like to open the question here. Yeah, what do you think? Will this next industrial revolution, Industry 4.0, will that be different? Who would like to start?
Sure. Yes, I think we should be having a much wider conversation with society in general about the potential future impacts on employment. I mean, clearly the rate of progress over the last 10 to 15 years in automation has been extraordinary. And although, yes, it's true in the past that automation hasn't led to wide-scale unemployment because people have been able to move from the traditional labor into new jobs in the service sector, it could be, it may not always continue to be the case. There have been studies which have suggested that anything from between 10% to as much as 50% of the labor force in developed countries are vulnerable to automation, and in developing countries it could be even greater. And what are the impacts of that? Clearly, employment is important, not just because that's the way in which we redistribute wealth around the economy, but it's also important for people's sense of identity. And these are really fundamental questions that we have to consider. We can't kind of blindly stumble into the future. So it's really important we have to look at the different scenarios and ask what if. How do we address some of these major disruptions, rather than leave it to chance?
So these are very broad questions, and some of them are a little bit hard to really assign like solid facts. But I think I'd like to hand over to Philippe, and maybe you can provide examples from Germany.
And what has come up in this discussion of the last part is that there's some sort of a time lag between the actual transfer of the technology into industry, and there's an educational process involved in this. So educating businesses how to use these technologies, and I think we're at the moment we are in this transitional period. And once these technologies that you've discussed or that you have hinted on are actually deployed within industry, I think this is the point where things start to get really interesting. And then we might see more of those labor market effects that we maybe not even can see in our statistics yet. And this will also apply to the service sector, because the use of artificial intelligence or new software is not yet understood to the full extent. Once there will be lots of more acceleration, I think, which will also shed employment.
Yeah, I agree. And actually, any technology that comes has impact on society. And it is really the industrial responsibility, social responsibility in deploying those technologies that becomes really important in avoiding those sudden problems that comes with new technologies. For instance, I don't know if you remember, do you remember when you used to go to the airport and you would have a customer at a desk and would check your luggage? And well, we don't have that anymore. We have so much automation in many aspects of service, and that is already happening. And I think robotics is going to bring another aspect of physical action on the world, where the robot is interacting with object and moving them and putting them together, doing things in the environment. Now, what is really new compared to what we had before is that the assumption is that these robots will be working with human. The difficulty to imagine is that these robots will be completely autonomous. Maybe that will happen eventually at some point. But in many of those tasks, we still need the experience, the expertise, the intuition of the human to be part of that process, especially when we're talking about physical interaction. And that brings a little bit of moderation that is you need to train people to be able now to get that support from the robot and cooperate and work with them. And I think that is a responsibility that as we transfer to those technologies, this is how we train workers to move from just carrying the full task to carrying maybe the cognitive part of the task. And I think there are many many examples where we see that we still need the skills of the surgeon. We still need the skills of the expert in each of those areas. But there are areas where we are now going to be able to go to, like resources, like all the oceans and the seas where we cannot go, we cannot send human, or all the accidents we have in mines where human can, should not be, but we are sending a human because we really need those resources. We will be able to create environment where robots are working together with the human in safe places, interacting to bring those resources. So I believe there are a lot of new applications that are going to bring new ways of organizing work, but in a collaborative way with the human. But that is not the only thing. I mean, there are a lot of other fears that are legitimate that we need to address and we need to work
sure.
to avoid.
I can see that's a positive scenario, and hopefully that's the way that things will develop. I don't know if you saw in the Financial Times this week, there was an interesting article about automation in the footwear industry, and Nike in particular is opening or has opened a new plant in Mexico run by Flex, the automated manufacturing company, where labor costs for making Nike sports shoes, labor costs have been halved, material costs have been halved, the supply chain has been enormously reduced. Many of the processes which involved a number of companies in the supply chain can now be compressed into a single factory, and the number of workers is enormously reduced. This is in response to increasing labor costs in Asia, and as production has moved from China, as labor costs rose, to Southeast Asia, and now labor costs are rising there as well. The option, rather than moving to, say, to Africa for even cheaper labor costs, is to go down the automation route. And it's not going to create an equivalent number of jobs elsewhere. It's looking like it's going to be a contraction. It also has the advantage of being close to the market, faster response times. The lead times from design to reaching the market has gone from months down to weeks. And this is, Nike is a company that employs over 1 million people in factories all around the world. The same is happening with Adidas and 3D printing of shoes and designed clothing. These technologies are with us now. Now, this will have huge impacts on developing economies where large millions of people are employed in factories, especially in the clothing and footwear industry.
Especially in these, as a developing country, you had the possibility in the past to dig into value chains that were spread all around the globe, and just specializing on certain components of the product in the end. This is possibly also going to be changed once technology provides for reshoring manufacturing and relocating it towards the design and the marketing of the product. That tends to be still a key component in the developed economies. So this could further cause some disruption in these particular countries.
Jonathan, since you mentioned the shoe industry, I have a story. So I have a project which is funded by the European Research Council, and this is an advanced grant about robotic dynamic manipulation. And those of you that know this project, we have a sort of a media expedient, which is a robot involved into the phases of the preparation of a pizza. So it's like a robot pizzaiolo. And last year, I gave a talk at an assembly forum, and it was an inspired engineer from the shoe industry that was interested into the possibility of manipulating the form of objects, like the dough of a pizza, and then the leather for the shoe industry. So now we have a PhD grant funded by the industry
in which we use cooperative robotics technology. It's not just replacing the workers, as probably Nike or Adidas are willing to do. It's like, you know, just in this kind of tedious and alienating jobs. But I mean, it's the new concept. And then we use some kind of techniques which allow recognizing and tracking the deformable weather and assist the worker in the gluing of the leather, like on the shoes. So it's like one example in which, I mean, no robotics technology was being used in the shoe industry. And honestly, you know, I was totally unaware of the potential of what I was developing as sort of blue sky research for the shoe industry. So those are, you know, I think the kind of examples that our community should really seek for in finding new operational scenarios where, you know, robotics technology and especially cooperative robotics might really just, you know, just raise the threshold in the sense of something which, you know, was done manually and also in a kind of handcraft manner.
Well, Bruno, I should tell you the truth. I would prefer the real pizza made by a human, and your pizza will never taste as good.
The robot doesn't have a soul.
Yeah.
That's whether it's a sentient and it's like...
To go back to the discussion, I fully agree. And as I said in the beginning, every technology can bring disturbing effect to the society, and I really think we have to take that responsibility. Fortunately, there is a delay. There is a delay where we can transform. I think progress, we cannot stop the progress of technology, but we really have to bring technology in a way where those disturbances will not happen. And I think the technologies that will come out of the new robotics that we are talking about is not automation in the sense that used to be before. That is continuous. That is happening now. Millions of robots are working around the world, and we have their effect already, and all of that is happening. But the new robotics is mostly about doing the things that we couldn't do before. And there will be also other effect that will reach other areas, but we have to take a social responsibility in making that introduction of the technology in a way that deals with those problems and avoid having those mass losses of jobs in places like in the developing world. That I agree fully with you.
Absolutely, and I can see that there's great opportunities with new robotics, but I think we're not thinking about the kinds of future technologies that whether we want them or not. And so, for example, we've spoken a lot in the last couple of days about the developments in humanoid robots and the enormous technical challenges there are in locomotion, grasping, seeing, language, and so on. Things which are enormously challenging for robots to do, but there's a lot of research going on. And yet, these are things that humans can do easily. And over the next, by 2050, there'll be an additional 2 billion humans in the world. Why are we researching things that humans can already do easily in order to make robots do them? Surely we should be thinking about how do we want to employ, or how do we give employment to people? Or if there isn't employment, what do we do with people? These are the kinds of questions I think that we should be thinking about.
I fully agree with that aspect, but I also feel looking back maybe, let's say, 1 or 2 centuries, every time there was a new sort of disruptive technology coming onto the market, maybe starting with a steam machine, people were always afraid that unemployment would go up. However, statistics history has proven that every time such a wave came in, actually unemployment rate went down. And
I hope that trend will continue. I think it would be irresponsible to leave it to hope and not actually plan ahead.
Fully agree.
We hope for the best, but plan for the worst.
I would, if you allow, maybe try to broaden the discussion a little bit. We have been focusing or talking or discussing a lot about the manufacturing industry, but robotics is more than just manufacturing. And one topic that many people talk about these days is self-driving cars. And just looking at like the logistics industry and also cab drivers, what will happen to this part of the workforce? And while I can see that there is fear, I'm very convinced that this technology will not come over us overnight. This will be a slow transition. And like we've seen in the past, I'm a true believer of a positive impact for the society once this technology comes to the market. That what we've seen over the past century or two, that this will even continue with the technologies that we're working on today.
Well, that is for sure. The discussion, I mean, this time, what is really different from developments in the past are that nowadays we can automate cognitive tasks to a large extent. And I think that's the key. I mean, if you consider the fact that Goldman Sachs is at the moment trying to automate 147 specific tasks of investment bankers working on an IPO. And these are so highly specialized tasks, and these sort of job profiles are only attainable with vast amounts of qualification. So, and this has implications on other sectors as well. And I think to a large degree, robotics is at the moment is of course software driven, and once it combines artificial intelligence with this capability, there will be a huge acceleration again in the ways to apply those technologies. And interestingly enough, you can see those effects mostly within or after recessions. And this is very particular about the German debate. We haven't faced a severe recession such as the US faced from 2008 onwards. And we had a small one within the manufacturing sector, but due to the engagement of unions, we were capable of leaving this small dip in the economy quite soon after. But if you have a look at the American labor market, you had huge effects, especially when it comes to upskilling, because companies had to introduce automation technology, and people needed to work with these technologies afterwards. That they were employed with lots of more demands towards their skill set. And this is something we can learn from. We can think about ways of establishing a tool that monitors how tasks change and how dynamically they change, and maybe to inform qualification programs afterwards. So it's really being able to react fast on changing tasks within the economy as some sort of solution to qualification demands.
You mentioned the word tasks there a few times, and I think there's what something came up a lot in the last couple of days was robots are there to automate tasks, not necessarily to take over entire professions. Yeah, I mean, you've talked about Goldman Sachs and they're automating a whole bunch of tasks, but okay, this will cause some reductions, but still there has to be an expert in the system or a human in the loop.
I have a concrete example.
Yeah.
The stock office is run by 2 individuals now, supercharged by computer engineers that provide the software. So the distribution of the workforce has changed. By now they employ I think 9,000 computer scientists and not that many banking specialists anymore.
Is the total number of workers the same, or has it gone down?
It's pretty much the same, actually. So this would be a proof from real life for this rather optimistic stance towards this debate. But still, I mean, when you consider the fact that software can also be written soon enough possibly by an artificial intelligence, maybe things go even wrong for them.
There is a difference with robots, and so we can take a specific task of playing chess, and we can get an algorithm that can search very deep and find and beat a human master. We can do that with Go. We can do that with specific problems in every specific area, and we don't need a robot. It's a computer executing a program. I think the difference with robots is the fact that robots are about not word processing, but about physical processing, interacting with the world, with the physical world, and creating actions that cause the world to change because of we're putting a robot with an object, moving the object, assembling and doing things. And that is a very different problem, I think, and different challenge.
Oussama,
so
I want to launch a provocation.
Yes, go ahead.
make a kind of strong statement now. I think that there will be more jobs lost because of artificial intelligence than because of robotics. I think robotics create job because you have the physical skills, you have the body action. Yeah. So this is much beyond machine intelligence because you have body and motion and action. Right. Yeah. And this is what really distinguishes what is AI, machine learning, machine intelligence from life and robotics.
Right. Yeah, well, this is not a provocation. This is what I agree with you. I mean, there is really a fundamental difference when we are attaching I mean, executing algorithms, but to perform actions that are based on sensors and skills and capabilities that requires so much knowledge and intuition and understanding that's still very far from what any child can do. So we should be really, I mean, making that clear difference. And as a result, I think there are great potentials of good use, but as with all technologies, there are also many ethical issues associated with every technology we introduce to the world.
Maybe just one more addition to the image you just created with a chess playing AI. I mean, this is something that we have solved for years. So you can play chess with an artificial intelligence system and it can beat the grand chess master. But what you cannot do today, at least I haven't seen it yet, that you have a mobile robot with 2 arms, you go to a shelf, you pick up the box with the chess figures, you open the box, you take the chess figures, put them on the board, and then play. So that is a physical interaction with the world which is not solved today. I mean, I'm pretty sure out there are many people who could actually do that now, but it's something that we have not really considered. So we have the intelligent, but not the physical interaction with the environment.
That's why we talked about the brain and the muscles, and this is the challenge.
I think this is an interesting distinction, but it's not really one that the public doesn't make a distinction really between AI and robotics. And in fact, in the popular press, AIs are called robots. And there is a very fine, I mean, what do you call, for example, image recognition AI that's looking at scans, medical scans, and an AI which is able to diagnose the scan that's linked up to a scanner? Is that now a robot or is it an AI? I mean, it's embodied in that there's a scanner and it can do the job of a doctor.
Yeah, I mean, the formal thing to describe about a robot is this connection between perception and action that is smart, intelligent, capable. So we perceive to act, and we observe the result, and when we act, we plan, and we understood the context and all of that. So really closing that loop with the world. And I think in the case of the different issues that come, so we need to sense, and to sense we sense tactile. Vision is a huge part of robotics, but the idea of just having a camera to monitor, to survey, without actually reacting to where things are is not yet a robot. It becomes a robot when the camera itself is moving and following and positioning itself in different locations. So there is an action, we call it active perception or active vision. But I don't think we really need to to go in every aspect of the technology that are dealing with this, whether the computer or the sensors. I think in robotics we have to realize there are challenges of physical interaction with the physical world that are very different from algorithms that are digitally implemented in a computer and running with a number at the end showing the result. And I think that difference is, is fantastic as a problem that robotics is bringing to researchers to explore, challenging researchers to solve those issues, but also to challenge researchers to think about potential applications together with the industry to see where these technologies can be applied for the good of humanity. And I really think there are areas where this could be wonderfully beneficial to humans, but also as I said before, every technology can be misused and can cause harm. But we really need to understand that difference, the physical and just the digital aspect, and then see all the potential of things that can be done with those machines and the challenges that those machines cause to research and to development and implementations.
I think also the physical side of automation, which is represented by robotics, can cause some harm. If you look at one of the most recent research that has been conducted by a research team, a joint research team in Germany led by the University of Düsseldorf, they had a look at data on the employment of robotics in the industrial sector, and they found, and it's drawn on the works of Darren Ashimoglu from the MIT. And so Ashimoglu and his team found negative correlation between between robotics and local labor markets. So people that were replaced had lots of troubles in finding work in these specific areas. Maybe jobs open up in different clusters, but for these respective areas, there were none. So the German researchers had a look at some data in Germany, and they found out that there was direct replacement by robotics, but those people that had been replaced in the company, they found work elsewhere in different niches of the company, but they had to accept most of the time wage cuts. So whereas the company was supercharged with regards to productivity and capital gains from this grew, wages pretty much stagnated. And since the 70s, we see a decoupling of productivity growth and wage growth. And this is a huge problem because this hampers demand within a society. This is where Germany exports so many products, because demand can't match with the productivity of the overall economy. And this is also linked to redistribution, of course, that is in a way affected because the capital gains flow to the production factor of capital, not anymore to in the same amount to wages. And this is even more the case for platforms, that business models that such firms as Google or Facebook choose to operate on. There you have lean worker structure, but huge profits that unilaterally flow to the production factor of capital.
My feeling is this is true. I mean, first of all, for the industrial example, the 70s and 80s, that was the classical automation, the conventional manufacturing, and that we went through that process, and that was the past. The new robotics is the one that will allow a surgeon to operate without opening the human body, saving recovery time and saving a lot of hospital bed time and saving money. The new robotics is the one that will save worker from dying inside a mine. I mean, this is the robotics I'm thinking about, not the robotics that will cut the jobs. But unfortunately, again, I mean, these are the potential things and disturbances that could come and definitely will come. And I think we are seeing them with other technologies. other technologies that do not use robots, but they use computers. And I think in that domain, we are seeing a lot of disturbances coming to society and to the working force.
I think this is a good example of how we see societal change being driven by scientific research and by a few corporations which are investing really heavily in artificial intelligence and automation. And this is why we need to be having this a wider, society conversation about it. And it really isn't entering into political discourse at any level, yet its implications are huge. We can't just sit back and hope for the best.
Yeah, which is why we hope to foster these discussions. If there hasn't been any questions until now, yeah, I've checked. There is no questions until now. I think what we've discussed, is that robots have quite a lot to offer, especially what you consider the new phase of robotics, being able to take on tasks which really are assisting us and augmenting our skills with human interaction and a human in the loop is quite different from the automation that we have seen up until now, which has taken away a lot of repetitive tasks. Nevertheless, I think you would agree also, Rainer, that there are still a lot of repetitive tasks that we could automate. Sure. So there are a lot of things where I think robots can help, but clearly there are also a lot of challenges for society as robotics, but also more importantly, probably as we've highlighted, artificial intelligence will have on the service sector. And clearly, we don't have the answers, but the discussions which we're having and the research which is increasing in this area, I hope it'll help to provide answers and to influence what people think and how we can organize ourselves in the future. I think with that, I would finish this particular panel for now. And thank you all for listening. All the information that we've been discussing today, you'll be finding commentary on this in our Nature publications. We're aiming to have a Nature outlook on this topic, Life and Robotics, published early next year. These videos will be freely available to watch on the Springer Nature YouTube channel from now on. Thank you all to the panelists, and thank you to our audience.
Thank you, Chris. Thank you. Thank you. Thank you.